So I decided to take a break from all the construction videos I've been doing and to look at integration. So integration is basically the opposite of differentiation. So in this video I'll cover the different ways that we can integrate different functions based on what the function is. So the first method of integration is just intuition. And that involves recognizing that the integral of a function is basically the opposite of differentiation. So I'll get into more on that later. The next method of integration is integrating polynomials. The next is using a U substitution. And then I'll also cover integration by parts and finally I'll cover partial fractions. So let's look at the first one, intuition. So let's say we want to find the integral of the cosine of x. Now the integrals we'll be dealing with are indefinite integrals, which means we won't have the numbers here and here for the integral. So we're not worried about the bounds. We just want to find out the function that is the integral of the cosine of x. So if you recall, d dx of sine of x is actually equal to the cosine of x. And since integration is the opposite of differentiation, we know that, or we can intuit that the integral of cosine of x is actually the sine of x, because the derivative of the sine of x is the cosine of x. Similarly, if we want to find the integral of 1 over x, we can use our intuition and know that the derivative of ln of x is the same thing as 1 over x. So the integral of 1 over x equals the ln of x. So just using a reverse idea or a reverse psychology sort of thing to determine what the integral of a function can be. Let's look at a few more examples of this intuition method. Let's say we have the integral of 1 over the square root of 1 minus x squared. This may seem quite intimidating, but we can still use simple methods to find its integral. So now recall that the derivative of the arcsine of x equals 1 over the square root of 1 minus x squared. So a function like this shouldn't scare you too much. We can just say that this is the arcsine of x. And obviously in each of these we'll have a plus c, and if I forget to do that, don't freak out. But there is a constant added to each of these integrals. Let's look at a slightly complicated integral that we can still solve using our intuition. The integral of 2x e to the x squared. Now while this is a great problem to use integration by parts, we can simplify it by just using our intuition. So if you think back as to what if you think about which derivative will give 2x e to the x squared, you can realize that the derivative of e to the x squared is equal to 2x e to the x squared. So the integral of 2x e to the x squared must be e to the x squared. And we can see that because d dx of e to the x squared, if you use the chain rule, gives you e to the x squared times the derivative of this part, which is 2x, which is the same as what we started out with. So in short, integration by intuition can help us find the integrals of simple trig functions and the functions such as 1 over x and the integrals of the arcsine, arccosine, arctangent, and also some e to the x functions in this format. Now let's look at the next way of or method of integration is integrating polynomials. So let's look at how to integrate polynomials using an example. So the example I'll use is x plus 1/3 x squared plus 2/5 x to the 4th. This is a simple polynomial. Now to find the integral of this polynomial, we follow a few simple steps. Now recall that when you integrate a function such as a polynomial, this integral can be split for each term. So this is the same as the integral of x plus the integral of 1/3 of x squared plus the integral of 2/5 of x to the 4th. Now, we can also pull constants out of the integral. So this becomes the integral of x plus 1/3 times the integral of x squared plus 2/5 times the integral of x to the 4th. Now all these integral symbols may make it seem a lot complicated, but trust me, this is going to make things a lot easier. So let's focus on the first integral, the integral of x. So when finding the integral of some term with x to the whatever power, in this case x to the 1, the first thing I do is I add 1 to this power. So x squared. But that's not all. Then we have to divide this whole term by the power that we have right now, which is 2. Following the same method for the next term, 1/3, we add 1 to this power, 2 plus 1 is 3, and divide that by that power, the 3. And the same for the last one. 4 plus 1 is 5, divide by that 5, and that gives you your answer. After some simplification, we find that the integral of this original polynomial is x squared over 2 plus x to the 3rd over 9 plus 2x to the 5th over 25. Let's look at some more complex polynomials where we can use the same method. Let's say, for instance, we want to find the integral of x minus 2 squared minus x plus 3 to the 4th. We can use the same method, just treating this inside the parentheses as our x. So first we distribute the integral to both terms. Then we raise the power of this number to 3 and divide by the new power, 3. And we do the same for this term. Let's look at one more example of polynomials. The integral of 2x minus 1 squared. Seems simple, right? Well, we can't use the same method that we used here, so we can't just add 3 and divide by 3, because we have a 2 in front of the x here, which throws things off. So one way we can approach this is to split or multiply 2x minus 1 times 2x minus 1, which gives us a result of 4x squared minus 4x plus 1. And now, using the method earlier, we can find its integral. Simply distribute the integral again, and that gives us a result of 4x cubed over 3 minus 4x squared over 2 plus x. Note that the integral of 1 is simply x. Now, well, that wasn't too bad. If we had a different power other than 2, say 908, we wouldn't want to multiply 2x minus 1 908 times. That would just take forever. So we have to find another way to integrate these types of polynomials. So to integrate this ridiculous polynomial, we can use something called a u substitution. Now what a u substitution is, we're essentially substituting u for some part of this function. So let's say u equals 2x minus 1, just for the sake of making things a little easier. Now what that does is it allows us to plug in u for this 2x minus 1. But recall that there is a dx out here. So if we find du dx, we get 2. Now what does that mean? That also means that du equals 2 dx. So we can substitute u for 2x minus 1 in here, but then we can also substitute du for 2 dx. So let's do that. Let's put in the integral of u, which we plugged in for 2x minus 1, to the 908th power, and then for dx, we'll substitute du over 2, because this gives us that the dx equals du over 2. Now the problem is with this 2 here. Now recall that when you have a constant in a term with an integral, you can pull out the constant. So let's pull out the 2 out front. Now, using the same method we used earlier for polynomials, we can integrate this as 1/2 times u to the 908 plus 1, which is 909, all over 909. But we're not done yet. We then have to substitute our 2x minus 1 back in for u, so we have it in terms of x. Now that gives us an answer, a final answer, of 1/2 times 2x minus 1 all over 909. And you can simplify that if you want, but this is the answer, and as always, don't forget the plus e. The u substitution can also be useful when trying to find the integrals of certain trigonometric functions. So let's look at the first one, the integral of sine of x times cosine of x. Now because these two are multiplied, we cannot distribute this integral to both of these. However, we can use a u substitution to find this integral. So what should we set u equal this time? Well, we know that the derivative of the sine of x is cosine of x. So let's set u equal to the cosine of x. And we'll see why in a sec. Then we want to find the derivative of cosine of x. So du dx equals negative sine of x. This also means that du over negative sine of x equals dx. Now remember, there's always going to be a dx over here. So now let's make our substitution. Let's plug in a u for cosine of x. And let's plug in du over negative sine of x for dx. And then we can cross out these two sign of x's because they're on the numerator and the denominator. But we still have this negative 1, which we can pull out of the integral because it's a constant. So this gives us negative integral of u du. Because everything is in terms of u, we can integrate this now. And since the integral of u is quite simple, it is u squared over 2, because there's an exponent of 1, and we just add the 1 to get the exponent up here and divide by the same number. And then don't forget the negative sign and the plus c. Then we have to substitute the cosine of x back into u to get everything in terms of x again. So that gives us cosine squared of x over 2 plus c. Let's look at another example of integration using u substitution. And let's take the function that we looked at earlier, 2x e to the x squared. Now when trying to find out what to set u equal to, see if you can find some part of the function whose derivative is another part of the function. So let's take this part up here, x squared. The derivative of x squared is 2x, which is part of our function. So we can set u equal to x squared. Then using the same method, differentiate x squared to get du over dx equals 2x, and then solve for dx. So your dx will equal du over 2x. And remember, there's a dx over here as well. So we can plug in u for x squared, integral of 2x e to the u, and plug in du over 2x for dx. And we can cross out these two 2x's to give us the integral of e to the u du, which, if you know your derivative of e to the x, you'll know that the integral of e to the u is nothing other than e to the u. Then we plug in x squared back into u, and we get e to the x squared plus c. Let's look at one more, slightly more complicated example of a u substitution. So I'll just do this in this little box over here. So let's look at the function x times the square root of x minus 1. So if we want to integrate this, we can use the same method. Let's set u equal to x minus 1. Then du over dx will equal 1, because the derivative of x minus 1 is 1. Then if we solve for dx, we get that dx is equal to du. So let's make our substitution now. The integral of x times the square root of u, substitute in du for dx, and we have this function, which should look a little strange, because it's not all in terms of u, so we can't just integrate this now. We have to do something about this x. Well, if we go back to this first equation here, which you can't see, we can see that we can solve this for x as x equals u plus 1. Then you can plug in u plus 1 for your x over here. And what that does is it gets everything in terms of u. Now we obviously can't use integration by intuition here, because I don't think many people know what the integral of this is right off the bat. But with a little simplification, we can make this into a polynomial. So we can say the integral of u plus 1 times u to the 1/2. recall that the power of 1/2 is the same thing as a square root. Then we can distribute this u to the 1/2 to the u and the 1. So u to the 3/2 plus u to the 1/2. Then we can split this integral into this term and this term to make our lives a little easier. And we're using the same method as before in integrating polynomials. We just add 1 to this power to get 5/2 and divide by the same power. Now dividing by 5/2 is the same thing as multiplying by 2/5. And this, since we've already integrated it, we don't need this integral symbol anymore. And we just do the same thing for this term. Add 1 to 1/2, which gives us 3/2, and divide by 3/2, which is the same thing as multiplying by 2/3. Then we just substitute in our x plus 1 back in for u. So 2/5 times x minus 1 to the 5/2 plus 2/3 times x minus 1 to the 3/2. And that's your final answer for the integral of x times the square root of x minus 1. So even if sometimes you can't seem to get everything in terms of u just by differentiating your u, try to resolve for x using this equation. And then plug that in for x and see if you can integrate that. Sometimes you may have to do multiple u substitutions where you might have to plug in v for u to try to integrate a function that you don't know how to integrate right off the bat. The next method of integration is integrating by parts. This allows us to find the integral of functions that have two terms multiplied with each other. So let's look at the integral of x e to the 6x. Now to do integration by parts on this equation, we first have to know what the formula is to find the integral by parts. So the equation is the integral of u dv is equal to uv minus the integral of v du. Now that may all seem very complicated, because it is, but we can make things a little simpler by just looking at what's going on here. So first thing to do is split this up into two parts. So one part will be x and the other will be e to the 6x. So we'll call u the x and we'll call dv e to the 6x. So u equals x and dv equals e to the 6x. Then let's find du, this component of the equation. So du equals 1, or du dx equals 1, which means that du equals 1 dx. Then let's find v, the other component of this equation. So if we integrate both sides, we get that v is equal to the integral of e to the 6x, which is 1/6 e to the 6x. If you're wondering how I knew this so fast, this is because you can use a u substitution. Set u equal to 6x, then follow the method that we did with the previous examples, and you should come up with this result. So now we have all four variables for this equation. Now recall that since we used u as x and dv as e to the 6x, we know that this is the same thing as this part of the equation. So we can say that the integral of e to the 6x, or x e to the 6x, is equal to u, which we established as x, times v, which we established as 1/6 e to the 6x, minus the integral of v, which is 1/6 e to the 6x, times du, which is simply 1. So now if we simplify this integral, or solve for it, we get that this is equal to 1/6 x e to the 6x minus the integral of 1/6 e to the 6x. So I'll quickly work out this integral on the side over here so you can see the u substitution once more. Setting u equal to 6x, du equals 6, so dx equals du over 6. Plugging that, remember there's a dx over here always. Plugging in u for 6x, and plugging in du over 6 for dx, we get everything in terms of u. Then we can find the integral of this, because we can pull out this constant 1/36 out in front, and since we just have a du, we know that the integral or the derivative of e to the u is always going to be just e to the u. So we get an answer of 1/36 e to the 6x, which we can plug in back here. So now this is equal to the integral of u, which we established as x, times dv, which we established as e to the 6x. So after all that work, we found the integral of this original function as 1/6 x e to the 6x minus 1/36 e to the 6th x. Now let's look at another example of integration by parts that may seem a little unusual. Let's look at the integral of ln of x dx. Now whereas with the first example, we had two separate parts, hence the term integration by parts. But here we just have ln of x, which we can't split up into ln and x because that doesn't make any sense. So at first glance, it may seem that integration by parts is a lost cause. However, we do in fact have two parts here. We have ln of x and dx. So we can set our ln of x equal to u, and our dv equal to dx. Then if we find the derivative of u with respect to x, we get it equal to 1/x. This means that du equals 1/x dx. And if we take the integral of these two, we get that v equals x. Then let's use the same formula over here. U dv, and the integral of that, equals u, which is ln of x according to us, times v, which is x, minus the integral of v, which is x, times du, which is one over x. Then, if we simplify this, we get that equals x ln x minus the integral of 1, which we know to be x ln x minus x. So even though the ln of x didn't seem like it had two parts to it, we know that dx can also serve as a part. Now the next question is, how do we know which part to set as u and which part to set as dv in our original setup here? Well, the answer is, it shouldn't really matter, but some ways are easier than others. For instance, if we had set x equal to dv and e to the 6x equal to u, it should have made a difference. However, if we follow through with that, we have to find the integral of x, which isn't too hard, and the derivative of e to the 6x, which isn't too hard either. So you should come up with the same thing. But let's look at this example. Had we set dx equal to u and ln x equal to dv, we would have to find the derivative of 1 dx, which is just 0. So if you use 0 in this equation, it doesn't really make sense in the end if you work it through. And if you had set dv equal to ln of x, you would have had to find the integral of ln of x, which is what your original task was in the first place. So it doesn't seem like a very wise move. So how exactly do you know which one to set as u and which one to set as dv? Well, a good rule of thumb is that whichever part you know how to derive easily, set it equal to u, because you know you're going to be deriving that. And whichever part of the equation you know that you can integrate easily, set it equal to dv, because you know you're going to have to integrate it. And after that, things should fall into place pretty easily. So the final method of integration is using partial fractions. We can apply partial fractions to many different types of equations. So let's look at the integral of 6 over x squared minus 1. Now to find the integral of this, we need to use this method called partial fractions. And to really understand what that means, let's look at a simpler example over here. 1/3 plus 1/2 can be also written as 2/6 plus 3/6 or 5/6. So we're going to use the same concept of splitting one fraction into two separate fractions. So let's apply this here now. How do we split this function into two separate fractions? Well, first, let's factor this denominator. So this equals the integral of 6 over x plus 1 times x minus 1. Then, we will set this 6 over x plus 1 times x minus 1 equal to two separate fractions. We don't know what those fractions are, but we can use variables to make two fractions. So let's say a over x plus 1 plus b over x minus 1. Then we will combine these two denominators to form one denominator. To do that, we'll multiply this fraction by x minus 1 over x minus 1 to give a denominator of x plus 1 times x minus 1. And we'll multiply this fraction by x plus 1 over x plus 1 to get the same denominator. And because the denominator is the same, we can say that 6 has to equal the numerator over here. So 6 equals a times x minus 1 plus b times x plus 1. Now our task is figuring out what a and b is. So let's plug in values for x to see if we can find out a and b. So let's let x equals 1. And I'll explain why we chose that in a second. In that case, if we plug in 1 for x here, this will drop out because it's 0. So what we have left is 6 equals b times 1 plus 1, which gives us that b equals 3. Then, let's set x equal to negative 1. If we plug in negative 1 for this x, this turns out to be 0, and this whole term cancels out. So this gives us that 6 equals a times negative 2, or that a equals negative 3. Now we can plug this back into our equation up here. So this equals negative 3 over x plus 1 plus 3 over x minus 1. Now we have to integrate this. And the best part about this is now we have two separate fractions, so we can split this integral between the two terms. Now we can pull out this negative 3 as a constant, and this 3 as a constant, so let's do that. Negative 3 times the integral of 1 over x plus 1 plus 3 times the integral of 1 over x minus 1. Now using the intuition method, we know that the integral of 1 over x plus 1 is the same thing as ln of x plus 1, because the derivative of ln of x plus 1 is 1 over x plus 1. So we can add this to 3 ln of x minus 1. So this is our answer. Negative 3 ln of x plus 1 plus 3 ln of x minus 1 for the integral of 6 over x squared minus 1. So let's go back here and talk about why we chose x equals 1 and x equals negative 1 for this step. And the answer is pretty simple. We want to pick numbers that will make the terms cancel out, or equal 0. So which is why we used 1, which makes this whole term 0 and makes solving for b much easier. We could have used any other number for x. We could have used a 3 here and a 5 here, but the problem is we have a system of equations, and it just requires a lot more work. Nonetheless, we would still get the same results for a and b. Using 1 and negative 1 in this situation just makes your life a lot easier. Now let's zoom out for the bigger picture on partial fractions. Where can we use the method of partial fractions? Well, the best place to use it is in this case, when you have something on the top and you have two separate terms here multiplied together. In this case, you can use partial fractions. Now, you want to make sure that the highest power in the top is 1 less than the highest power in the bottom. So the highest power in the top here is 0, and the highest power in the bottom here is 1, which makes it a good case and a good candidate for partial fractions. Let's say we had something such as x squared over x plus 1 times x minus 1. This would be a bad case for partial fractions because our power in the numerator is 1 more than the power in the denominator. So that concludes the video on integration. If you have any more questions about integration, post them in the comments section. Hopefully I'll take a look and try to respond to them. Until then, have a great time.